we want to prove that the magnitude of A cross B equals magnitude of A times magnitude of B times sine of the angle between them. And first thing you want to do is square both sides, because it allows us to use the Pythagorean identities, which is extremely useful here. Okay, now I haven't liked other videos I've seen on this because I like to memorize proofs, and the other ones require you to remember several expressions and steps to start with, and then they tie it together later, and I don't want to work that hard. So I've simply tweaked the same proof so that I only have to remember one thing, and that is how to start. And everything else is a natural progression of thought, not a bunch of memorized steps. So if you just remember where to start and then you practice this a few times, I think you'll see that it suits anybody who likes to remember proofs. So the starting place is simply this. Well, actually, I'm not going to use a parenthesis yet, but it's going to be simply the dot product. So we're using this as a given. I'm not going to prove the dot product. Basically, the law of cosines gives us the dot product. The dot product then gives us something called Lagrange's identity, which we'll see in a minute. And Lagrange's identity gives us the magnitude of the cross product. So, but I'm accepting the cosine identity here as a given. So our starting place is this squared. Be sure to square it. And now just start working it. And we know our trig identities allow us to do this, and now I'm going to distribute the magnitudes in. And this is what we wanted. We now have the same term here as in what we're trying to prove. And we know that this is equal to all of this. So now I'm just going to rewrite down here with the sine term isolated. Okay, let me just make sure I've copied everything and moved it around correctly and stuff. Okay, so this is a true statement here because we're getting it from the dot product. And so I'm going to write up here the stuff on the left. And this is a given. It's true. It's established by the dot product. And this is a question. I should put question marks on here since this isn't proven yet. Okay, well, now if you look up here, we know this is equal to this. The natural question arises, is this equal to this? Because if we already knew that, we could then say, well, then this has to be equal to this, and our proof would be done. So that basically is now the focus of our proof. So let me line this off, and I'm just going to write down here the equation, this is equal to this. and this is not established. This is now what we're trying to prove. If we prove this, we will have our original hypothesis proven as well. So this has a name. It's called Lagrange's identity. I'm not going to write it out. You can look it up. But basically, Lagrange's identity gives you this proof of the magnitude of the cross product. So now this is what we're focusing on. The only thing I'm going to do is I'm going to move this over to the left so that it's positive. If you forget to do that, it's not going to hurt anything. I just like it better that way. It just seems cleaner to me how everything comes out. And okay, I'm going to box this because this is all we care about now. And the videos I've seen before, they tell you to remember this term and this term and this term, and then to, algebra them all out into their basic properties so you can compare them, and it all ties up later. Well, I don't want to remember these three things. I don't want to remember Lagrange's identity. I want to derive it when I need it. So basically we have the job of expanding this out, and this out. We've got three expressions to expand, and that will allow us to see if this is true. I should have put a question mark here. Okay, so let's take the first one here, which is just going to be magnitude of A cross B, and let's expand it out. I'm assuming you're watching this video because you're already familiar with taking cross products and dot products and magnitudes, and you know the basic properties of vectors. If that's not the case, then you may need to look at some other information in some other videos. So if we expand this, we're going to be taking vector A, its components, and crossing those with vector B, and taking the magnitude of that squared. And when we do this, remember the cross product always gives us a vector, not a scalar quantity. So when we do the cross product, let's see, we're going to get A2B3 minus A3B2, and then A3B1 minus A1B3, and A1B2 minus A2B1. Let me just check that I did that correctly. Okay, I think that's it. And that's going to be equal to some stuff in 3 parentheses squared down here. Again, that's just, it just comes from taking a magnitude, and I'm assuming you know how to do that. So basically we're just copying this into here, second term, second parenthesis, third term, third parenthesis. So it's just a matter of copying now. I like to do stuff like this because it seems to make me a little more stable and less prone to careless errors, and plus it just seems easier anyway. So we got a 2332, and then we have a 3113, and then we have a 1221. Okay, now I got a lot of foiling to do here. This proof involves a lot of tedious algebra. So I hope it's not too confusing, but what I'm going to do, you do FOIL, first, outer, inner, last. I'm only going to do the first and last terms of each parenthesis to start with, and then I'm going to come back to the middle stuff. So this first parenthesis, the first term here, I would have a2 b3 squared, and the last term would be a3b2 squared, and I'll come back to the other stuff later. Looking at this one now, I'm going to have I'm going to have that, and go into the third parenthesis. Okay, now I got to go back to all the stuff I didn't get. So back to this first parenthesis here, we know it would be a -2, and then you can verify it would just be 23, 23. And then when we come to this one, so I've taken the two middle terms and I already combined them. When we take this one, we're going to have a -2, and then this term times this term. So what I'm going to do, since I know that each parenthesis is going to have a -2 in it, I'm going to factor that out right from the start. So now this middle term here with the 2 already gone, we're going to have 13, 13. And then this one, we're going to have 12, 12. So if you think about the numbers 1, 2, and 3, you'll see that if you think how many different ways you could take pairs out of 1, 2, and 3, well, you see them all here. You could have 2 and 3, or 1 and 3, or 1 and 2. So it might be helpful to sort of keep track if you did things right. Now we have that this is equal to all of this. And we're done with the first expression. Now we've got to get a dot b squared and expand it. And just for clarity, I'm going to make two parentheses first. Okay, so if I dot vector A with vector B, I'm going to have its first two components multiplied, a2b2 plus a3b3. Okay. Now I got a lot of distributing here to do, and I'm going to do similarly to the previous one. I'm going to take the first two terms squared, and then I'm going to take the two middle ones, so that's going to make a square, and then the two third ones. You'll see why later why I want these grouped like this. So now I got to go back and get everything I didn't get. So let's take this term, and I've already taken care of the first one here, so I need to do put this one with the second term. So that's going to give us that's just going to give us 12, 12. So now I have this one and this one. Now I need to get one with this. So that's going to give us a 13, 13. And we're done with this one. Moving on to this one, I already did the middle term here, so we're going to have to do this one and then this one. So this one's going to give us another 12, 12. And now this one and this one, that's going to give us a 23, 23. And now we're done with that one. And moving on to this one, now I'm going to get something from here, something from here. So we're going to get a 13, 13. And a 23, 23. So you'll see that these come in pairs. And so what I'm going to do here, I'm just going to put a 2 in here, put some parentheses, and I'm going to erase everything down here. I basically just did all that so you could see where it came from, because this stuff can get pretty confusing. And now we have that this is equal to all of this. Okay, so you'll remember we wanted to add these two together. We've expanded this and we've expanded this, and we're going to add them together, and we want to see if that's going to equal this. So we'll come back to this term later, but I'm going to add these first. It's pretty easy. Basically all I'm going to do that is just look what happens, something cool when you add these together. This, all of this, and all of this are going to disappear. And so when you add these two terms, you're basically just going to get this group of stuff times this group. And so everything circled in the blue, that is this plus this. Now, our last term is going to be magnitude of a squared, magnitude of b squared. And hopefully you are familiar with this identity. Vector dotted with itself equals its magnitude squared. So I'm just going to be using that. And so if I dot a with itself, it's just going to be a1 squared plus a2 squared plus a3 squared. Same thing with b. And now I got a bunch of distribution to do, but this one isn't as bad. You're going to end up with 9 AB terms. So 1, 2, 3, 8, 9. And so if we look at this first term here, it's going to get used 3 times because it's going to be paired with B1, B2, and B3. So we need to make 3 of these. And then B1, B2, B3, all of them squared, and we're done with that one. This one's going to get paired also 3 times. We're done with that one. and we have that this is equal to all of this. And now, the big thing we've been leading up to that we want to establish is this group, everything in the blue, is that equal to all of this? And I don't even need to write it out. We can just cross stuff off. So let me get a different color here. And so I'm just going to start crossing stuff in this group off and matching it to something up in one of these two groups. So I crossed off the 11s. Now I have a 12. Do I have a 12 up here? Yes. 13. This is where you hope you didn't make careless mistakes. 21. 22. 23. 31. 32. And 33. And you can see these do what we wanted. This plus this equals this. So coming back up here, that's what we wanted to prove. This plus this equals this. So this is now confirmed. Let me get a different color here. This is proven. So how does it help us? Well, that's what we wanted to know. We wanted to know, is this equal to this? And that's true. We've proven that now. And so we can say, since we know this is equal to this, and we now know this is equal to this, well then this has to be equal to this, and it is confirmed, which proves the square rooted version. And so that's it. That's what there is to this proof. However, I do want to do one thing before closing the video. So this is when we're done if you're not interested in this. But I want to take the Lagrange identity here and show one final thing. I want to show that you can actually do the proof straight from Lagrange's identity. Not so much because I'm interested in the proof, but I want you to see very clearly the relationship. So let me just put a line here and clean it up a little bit. Okay, so we have Lagrange's identity, and we just start working the right side. So when you prove straight from Lagrange's identity, it's very fast. We know the dot product is equal to this. And now I'm just going to distribute the 2 exponent in. And now I'm going to factor the magnitudes out. And we can use our Pythagorean trig identities. And we see that if we start with the Lagrange identity as a given, then we get, we prove what we want. And of course, then you square root both sides. and you've proven it. But I personally am not interested in starting from Lagrange's identity because you're right there anyway. I'd rather go farther back. So the chain of proofs is basically this: the law of cosines gives us the dot product. I'll just write it like that. The dot product gives us the Lagrange identity, and the Lagrange identity gives us the identity of the magnitude of the cross product of two vectors. So what we did today, we started from here as a given and went to here. But if you want, you can start from the Lagrange identity and do the same thing. I don't prefer to do it because this is already, most of the work is done anyway. This is right here. So I prefer to go back farther myself.